All right. So, okay. I wanted to start by talking very briefly about some of the things we learned about capacitance, some of the things we've already learned about resistance, and some of the things that we're going to learn about resistance and circuits. Just kind of like a review to check where we're at, what pieces we need, and I need to wait for this thing so I can hit the pause button right about now. So give me just a second. Oh, it's still hung up there, waiting for the okay. There it is. All right. All right. So let's first start by reviewing some things about capacitance that we've learned. Can you see that in Zoom land?
It's good.
Okay, thanks. All right. Does anybody remember some of the types of problems? Just to start spewing information. Anybody remember anything that we did in the capacitance chapter? Yeah, series versus parallel. Sometimes we call those capacitor networks. Get that there, get this here. Right? So, and some of the things that we did, we used Q equals delta VC, and U equals 1/2 Q delta V. And so the things that we studied were basically Q, delta V, U, and then capacitance itself, right? All right, so that was one type of problem that we did. What was another type? Maybe remember we talked briefly about dielectrics? And I called those sometimes dielectric in-out. And the other one were those charged caps reconnected problems. And I don't know if you recall the point of those problems. That might have gotten kind of buried in there. The idea was this brought the concept of charge conservation kind of to the forefront. And sometimes we talked about energy conservation for single loop. And I'll even specify it even more. It was energy conservation for a single loop around a circuit in a steady state, meaning it's not changing. And energy conservation for us in this blah, 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 this long set of words basically meant we were talking about the changes in voltage. So we're talking about charge Q and voltage V in this way. Those were some big kind of concepts. And if you recall, we were saying, oh, delta V on this capacitor has to equal delta V on that capacitor once it reaches equilibrium. And that's what we called conservation of energy for those types of problems. That's all that means. Do you remember anything else we did?
Measured the capacitance for different types of things.
For different shapes. One other thing we did was determine C, I'm going to say from geometry. Okay, that's what we did in there. And so do you remember the process? We started off by knowing what property or what thing started this whole chain. With the electric field from memory, meaning a memorized result, or Gauss's law, right? So that was one of the things that we did. And then from there, you figured out delta V. And then from there, and delta V was something like minus the integral of E dot ds. And then from there, what's that?
Sorry, could you zoom into the left board, please?
Yeah, sure. All right. I was hoping to do it all on one big, but we could go back and forth.
The red
Sorry,
is
it's just a little blurry.
Yeah.
The red are all the other colors okay? It's just the red?
Yeah, it's just the red up there.
All right, well, let's do this for now. Does that help for now?
Yes, that's good.
All right, better to do it than not. All right, and maybe I misspelled geometry. I don't know. That looks weird to me right now, but I don't care. Yeah, all right, so I was focused. It looks weird, right? Whatever. All right, so then from here, what did we do? I forgot. Oh, we used, yeah, we used Q equals VC. Solve for C. So that was what we did in capacitance land. So now let's do the similar types of things, and maybe there's going to be a few different ones for resistance. So we'll do that on the other board here. So I'll go out to here. Again, we'll keep that in mind. Let me do this again. Right? Oops. So again, you may not need this board. I know the red is hard to see. We can zoom back and forth. But for resistance now, can you see that okay on Zoom?
Yeah, that's fine.
Okay, so we'll just get rid of this for a while. All right. So what are some things we learned last time about resistance? Remind me. Anything? Any equations? Yeah. So we're going to have delta V equals IR. That was Ohm's law. All right. There was another equation that went with that. Oh, true, Joe. But power, poison, IV. Right? This was power. Right? I don't know if you could tell. I'm trying to set this up to look the same as what was here. So now we haven't done this yet, but guess what's coming soon? Networks. All right. So that's going to be chapter 20. What chapter are we in now? 6? So this is the next chapter, chapter 27. These guys are discussed in both chapter 27 and 28. All right. But resistor networks, it'll be the same type of thing. We'll try to get to that today at the very end. All right. Notice the main difference here. With these problems, we were finding these variables Q, V, U, C. Now we see we're looking for I, V, P, R. So it's very similar physics. Remember that power is energy per unit time, and current is charge per unit time. So that's where we get the derivatives are hidden inside here. This is du dt. This is dq dt. Whatever. All right, so there was that. What was something else we've already covered? Do you remember anything else?
The temperatures.
Resistance and temp, right? And so that was R as a function of temperature is equal to R naught times 1 plus alpha delta T. We had those type problems. And this had their own set of problems because this was that whole emphasis on 20 degrees. And this was T final minus 20 degrees. Still okay on the text size on Zoom?
Yeah, that color's fine.
Got it. Next. And I guess we also talked about resistivity as a function of temperature. Was resistivity at 20 times 1 plus alpha delta T? Which, how did resistivity relate to resistance? Remind me. What was the equation we used? Area. Nice. So we used this kind of information. So all of this is chapter 27 here. That was all chapter 27 stuff. Huh. Well, I know those of you on Zoom can't really read this one. It was determined C from geometry. What do you think the equivalent thing we would do in the resistance chapter is? Determine resistance from geometry. So this is also chapter 27. I'll give you a hint. R is equal to the integral of dr is what we're going to use. Shocking. But this equation down here can help us rewrite this. That's the integral of rho ds over the cross-sectional area. I guess I should mention here, this was a big deal. We emphasize this over and over and over again. Because of the definition of current, we kept having to remember this was not just any old area, it was the cross-sectional area. That was a key factor. All right. And then I'm going to go ahead and tell you two other things. Basically, you don't know what these are. This is chapter 28. Oops. Wait, this is chapter 26, wasn't it? Sorry about that. And this was chapter 26.
Right.
Sorry about that. So that means this is going to be chapter 27.
So would that be chapter 26 and 27 for the resistance up to left?
Yeah, this should be 6 and 7. Sorry, I'm getting my chapter numbers off. Thank you. So 6 and 7 and 6. Thank you. And then another thing that we're going to learn are called RC transients. Now I like to bring, all right. The idea here is, and this is also chapter 27. Some of this stuff is where we're going. Some of this stuff we've already done, but it's kind of all one big package. And that's why I wanted to have both boards here and show it all on there. I don't normally like to do that. The idea is we learned a little bit about capacitance. You probably don't feel that good right now because you don't really understand it. We're starting to go through resistive circuits, and I feel like by the time we finish some of this stuff, that stuff will make more sense as well. So if you're feeling a little bit lost or in capacitor land as you're doing the homework, that's typical. All right. So I think we're ready to, I don't know, hopefully any questions about this? This is the big picture, where we are, where we're going. Let's get to it, right? Let's do some examples. I want to mention a couple of things here. Before lab tomorrow, if you want to enjoy lab tomorrow more than, endless suffering, I recommend on page 108 and 109, look at 26.10 and 26.11. These show you some graphs that are very typical of what our graphs are going to look like tomorrow in lab. So if you can look at these questions, even if you have the solutions open and just kind of walk through them and read through them, or know that these are available and have them in lab open and ready to read, that's going to help you understand lab tomorrow. As a result, we're going to focus on that stuff in lab. I'm going to skip to the next page, 110. We're going to try 26.13 and see how you do here. 26.13. I'm going to erase the board and get ready to go. You guys can look at 26.13. You can talk as much as you want, if you want to, or just read and start sketching it out. You guys like it when I do those mini reviews like that, just kind of big picture? I know that doesn't do an actual problem, but you can always tell me if you don't like stuff I'm doing, send me an email like, I wish you would do more of this or that. Can't always help you, but I'll try. $26.13. Kind of looks like a cigarette. Okay. Side note. What is the largest number of cigarettes you can have in a pile such that each cigarette touches all other cigarettes? You understand the question?
Yes.
Work on that for next time. All right? It's an interesting answer. All right, so, okay. Now, in this case, let's say this is length 1. This is length 2. I guess I'm gonna assume this is carbon. Is that what I called it? And this is nichrome. It doesn't really matter. And then what else are we told?
The resistivity.
Resistivities of each and the temperature coefficients of each and the radius. So I'm going to specify the radius like this, where R is equal to, what was it, 0. What? 500 millimeter?
2.0 millimeters.
What?
For each year.
Oh, 2.0. Okay. I must be thinking of a filament problem or something. Okay, 2.0 millimeters. Got it. We're told resistivity 1. That's the carbon. What was that value? 3.5.
Times 10 to the negative 5th.
10 to the negative 5th. Whoa. What are the units?
The weird horse shoe.
Oh.
Yeah.
Oh, meters.
Oh, meters. Oh.
Yeah, you said ohms.
Oh, yeah. Okay. there's-
Right? All right. And then alpha 1 was,
1.10.
got it.
times-
Wait, no, that's not alpha 1.
Oh, alpha.
Alpha is the temperature coefficient.
Oh, okay.
Ooh, it's negative. And then what were the units? Times 10, 10 to the minus 3. 1 over degrees Celsius. 1 10 to the negative 6. Point 4. All right.
I see the second resistivity as 110 times 10 to the negative 8.
Yeah. Okay. So do you agree that's the same? 1, 2.
Oh, yeah. Never, yeah.
Yeah. Different versions of the book might have that written differently. Sorry if mine's old. I don't know. All right. Or if are you looking at the table on the back?
No, I was looking at 2613.
Okay, yeah. It turns out nichrome in particular, yeah, so there's many different types of nichrome, as we'll learn in lab tomorrow. Okay, so more on that tomorrow. All right, good enough for now? You good?
Yeah.
We have one last piece of information. What do you think? We're told that we want this to remain constant. As the temperature changes. Well, remind me. When a wire heats up, what happens to its resistance? Does it go up, down, stay the same? It depends, is the correct answer. If the wire is made out of metal with a positive value of alpha, the resistance should, as temperature goes up, what happens to resistance if you have a positive value? It goes up. Remember, what was the equation? The equation for that resistivity as a function of temperature was rho naught times 1 plus alpha delta t. Look at the equation. If alpha is positive and delta t is positive, rho gets bigger. Similarly, if alpha is negative, as t goes up, this gets smaller. So the answer to what happens to a wire as it gets hot, the answer is it depends. Gee, I wonder if that's on a midterm or a final or both. I don't know. I get people every year with that one because I say, what happens to the wire? And I either semiconductors, the resistance tends to go down because as you heat them up, there's more thermal energy to jump the band gap. If you don't know what I'm talking about, ask me later. Okay. All right. Any ideas how we might approach this? We want the resistance to not change. We've got all our formulas up here. Or some of them anyways. I don't know. What would you guys tell me to do here? A lot of times students, when they first see this, feel like there's not enough information, right? Feels like something's missing. Obviously, you could look up the answer and the solutions and write it down, but I actually got this from a 142 class, algebra based, and it like snows people every year. No pressure. You guys are supposed to be the smart ones, right? What's that? R equals, okay, so there's an equation we don't have up. R equals rho L over area. All right. Do we know the lengths?
Yeah, roughly, we know L1 and L2. Like,
Do we know them?
not necessarily.
We don't have numbers for those. That's what, or is that what we're trying to figure out here?
Correct.
So, okay. Well, do I know resistance 1 or resistance 2? No, that's the problem. Right? We don't know, there's too much we don't know. I don't know L1 or L2 here. Right? So, and over here, I don't know the individual resistances, so that doesn't help. Huh. No, that's a good idea. It's not gonna work. What do you think? We got to use this fact. How can we employ this fact? Right? This is what physics is all about, taking words and then doing something with them, right? And saying, oh, well, that implies something. What does that mean to you? In terms of, can we get an equation out of that fact? What?
You want them to change by the same amount?
Close, very, very close. So wait, you said you want them to change. What's a way we write change in resistance 1?
Delta R.
Delta R1. He said, I want them to change by the same amount, right? That's not quite right, is it?
Magnitude.
Yeah, or said another way, don't you want this one to change by the exact opposite amount? If this one goes up by 3 ohms, we want that one to go down by 3 ohms. Excellent. Well, wait a minute. What is delta R1? Let me help you. There's a resistance version of this. That's the resistance version of that equation. Which part gives us the change? Is it the first term or the second term? The second term is the change. So what you just said is R1 subscript 0. I'm trying here. Alpha 1 delta T1 should equal negative of R2 subscript 0 alpha 2 delta T2. But wait a minute. If these two things are in the same room here, the temperature changes should be the same. The amount that this one changes should be the same as the amount that one changes. They're connected together. They're in thermal equilibrium. We hope. That's going to drop. How do I get length into that equation?
R equals rho.
The equation Jesse brought up. So we did need that. So let's put this over here. And that gives us rho 1, length 1 over area 1 at temperature 20 degrees. Somehow stick that in there. Times alpha 1 should equal negative rho of 2 at 20 degrees. I'm sorry, my subscripts look so bad here. Length 2, alpha 2 over area 2. Wait, what else do they have in common? Area. So the area drops out. That's going to cancel. What about this minus sign? Semiconductor, metal. And that's how the minus sign ends up matching out with your magnitude equation. Remember he suggested, why don't we just take the absolute value? I'd agree. The absolute value would get rid of those minus signs and you would have gotten it. You could also do it this way and we see the minus sign drops out. Cool? Now, this gets us one equation for the lengths. Here's the other equation for the lengths. Now we have two equations, two unknowns. You can plug in this same equation up here and get the job done. Does that make sense? System of equations, two equations, two unknowns, you crank it out. I gave this to my 142 class once, and just they died. The moral of the story here is sometimes it's convenient to think of these equations as resistance as a function of temperature and write them out the long way. Sometimes it's better to just think of the change in resistance being the second term.
Sure.
Everybody good on that? Ish?
Yeah.
Good-ish. So you could take that home and try and redo it. And if you wanted to practice, you could try the one right after. I basically wrote a different version of that one for the parallel type of circuit. This is in series. And I don't know if you can tell, basically because length is in the numerator, when you have series resistance, you just add them up. I'll discuss that more at the end of class. Sorry, we haven't talked about that yet. What do you think? Good enough? Yeah, question.
How do you get change of R1 to equal that?
Oh, remember, if I could, I'm gonna write this here. Sorry, I'm running out of space. Right? We agree that resistance as a function of temperature is R naught times 1 plus alpha delta T, right? Well, when I write that out, that's resistance is R naught, that's at 20, that's the annoying thing, plus the idea here is this is the value at 20, this must be the change delta R.
Oh,
Is that what you needed?
Yeah.
Yes.
Okay, that makes sense.
So this is the part associated with the changing temperature. That's the part I'm going to call delta R. Good comment. You guys see that over the monitors? Are you good?
Yeah.
Good enough? All right. Good question. All right. So this begs another question. I don't know if you remember last time when we were here. So I'm going to move on now. Last time we were here, remember I brought in that wire and it got hot?
Yes.
Did you notice the wire start to sag a little bit?
Yes.
As it got hot, it would start to sag just before it broke apart. So I wanted to ask you about something. As temperature goes up, what happens to lengths?
Yeah.
They increase. There's an equation that you're going to learn in Physics 162, or that you already learned, that looks nearly identical. Do you remember that? You don't need to take notes on this part, anybody, if you want. Okay, this is just for knowledge. Okay, so I wanted to explain a subtlety that some of the 162 people might have been wondering about. I don't know if you know this. Areas. That's a length times a width, right? Now maybe you don't see this right away, but there's going to be an alpha in the length. There's going to be an alpha in the width. And then it turns out not to be squared you're going to get a length times a delta term, but you're also going to get a width times a delta term. But the delta term times a delta term is so small, it doesn't matter. It's like dx times dx would be very small. So it turns out this goes to area naught times 1 plus 2 alpha delta. It basically doubles, not squares. All right, and we can discuss that more later. I'll work it out if you need it. But the idea is lengths are going to increase a little bit. Areas are going to increase twice as much. Okay. So now in this case, let's look at our equation. Resistance equals rho L over area. When it gets hot, what happens? And let's assume we're talking about metal. So we're talking about a metal now. If we're talking about metal, as this gets hot, what happens to resistivity? It's good. What? Up, down, stay the same. Up for metal, down for semi. Okay, what about the length? What about the area? Up twice as much. Shouldn't those factors cancel out? The issue is if you start actually looking at the numbers for these values of alpha, the numbers for thermal expansion of lengths and widths are much smaller than the resistivity expansion. Resistivity changes by a lot. These numbers are much smaller. So it turns out it's actually much more like this. Double a really small thing. And so as a result, we did see the length go up. That's why the wire started to sag. But it's pretty negligible compared to the amount the resistivity goes up. So in general, in case you were wondering, you might have expected that, wait, since the area goes up, maybe it should actually decrease in resistance. But no, the length and the area don't change by a substantial amount compared to the resistivity. Everybody good on that? Okay. Does anybody know a material that doesn't increase in size when you heat it? Said another way, is there a material that increases in size when you cool it? Water. From 4 degrees to 0 degrees, right? Water actually increases. It's a special material. Why fish don't die in a lake when it freezes. Anyways, that's kind of a fun exception to what we've just been talking about. All right, good enough. I think that's just for fun and just to make sure you understand that. All right. I'm ready to go on to page 112. The other problems you can look at, if you're curious about how this relates to thermo, 26.17 is an interesting question that relates to thermo, but yeah, I'm going to gloss over that. Okay, I've got to erase the board. I want you to read page 112 while I erase. Read page 112. Any questions from Zoom? Are you good out there?
All good?
All good? What do you think of the Zoom versus in person? I'm just curious. Is it good enough?
Yeah, it's good. I was going to come to class, but I had a lot of stuff going on, so I just logged in here.
Is it kind of nice being able to have that as an option?
It is, yes.
Right on. Okay.
I get the luxury of going home and sleeping.
Yeah, it's worth it, right? If you could sleep, I mean, it's probably easier to stay awake through a boring Zoom lecture than tired in person, right? So if that works, hey, cool. I'm glad that something I'm doing is actually useful. All right. Now we're up to this new topic. Resistance from geometry. Our claim is resistance should be the integral of a small amount of resistance.
I think you need to switch the board for a second.
Thank you. Thank you. Which in the workbook, I say it's something like rho ds over the area. All right. Now, what does this mean? I want you to think about something here. let's say we had a wire and there's a bunch of tiny resistors in here. This is DR1, this is DR2, this is DR3, this is DR4. Let's say we take one wire and we build it up out of 4. You would have no trouble telling me the total resistance is the sum of dr subscript I from I equals 1 to 4. You would have no trouble with that, right? Isn't that the same thing as saying the integral of dr? We're adding up the pieces. Why does it work this way? Well, think about it. If this was the same wire, we know that this one would be something like rho length 1 over area. And if let's assume they all have the same area for right now. We get a bunch of these dot, 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 dot. So this would actually look like that. The idea here is the resistivity and area are macroscopic qualities, right? Rho is a property of a material. Area is not some tiny little thing. It's the cross-sectional area of the wire. Worth emphasizing. All right. And the idea is what we're really doing is we're adding up these little lengths. What's powerful about this is when we write it this way, this can handle non-uniform density or an area that's non-uniform. For example, all right. Here is a slab that you can't see at all, but the idea is, what if I was trying to flow current through this device, right? You could imagine, this is exaggerated now, but maybe the input side has this small area right here, and the output side is here. We have an area that's changing. This would work. Same with this weird shape, right? Right? You can have different cross-sectional areas depending where you're at. Right? Or imagine this is a large piece of semiconductor, right? You could actually take a device and you could implant ions inside of it. The ions that you put inside of it would change the resistivity at different spots in here. So this could be some function. And that's actually useful in chip physics, perhaps. This might be useful again in chip physics. So if you're designing tiny little circuits, this is not outrageous to think it's plausible to do this. Now, most of you might think, I'm never going to deal with this. And that, because to be honest, is true for most people here. However, I do think some of the math that we're doing relates to many branches of engineering. And the concept itself of saying, look, add up the pieces using an integral, that's fundamental to everything in engineering, right? So hang in there if you don't like this. Let's try and get through it. And I do feel like the math does have some applications in a wide branch, in many branches of engineering and science, okay? Now, I do have some bullet points here. Look at the very first bullet point there. I'm going to change that one to avoid at all costs. I hope you agree there's no reason to do an integral if we don't need to do an integral. So look at the problem. The first step of using this equation is know that you actually have to use it. 2, what's the next one? What does this look like? Well, in case, let's do this one, right? Let's say I have this shape. I'm going to draw it up here, right? So, I don't know, or let's just do a cylindrical shape. Okay, let's say we have a cylindrical shape. That's just easier because we'll start from what we know, right? Now we're going to assume that current typically in the cylinder is flowing along the long axis of the cylinder. Does that red pick up on Zoom?
Yeah,
That
that's
one's
fine.
clear.
Yeah, so it must have been that other red was dying. Okay. The trick here is this is supposed to be a cross-sectional area, right? So now, rather than thinking of this as a resistor, 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 the idea is this, we're building the entire cylinder out of tiny cylinders. In this particular example, the thickness of that would be dx. However, most of the time, when you see this, if you see a small thickness in the horizontal direction, what do we immediately change it to? This is equal to dx for this problem. On another problem might be dz or dy or dr or something, right? So ds is kind of a placeholder here. Notice the ds and the a depend on current flow. Okay, so when you're doing these problems, the direction current flow determines a and ds. So I think that's what I'm saying in bullet 2. So I'll say it a different way. It has to be a cross section perpendicular to current. Or if you wanted to talk about that, you could say the area vector points the same way as current. You remember that area vectors point perpendicular to the surface? Basically, the current has to be a cross section. Yes.
From this equation, ds is a scalar value.
Yes. ds is a small amount of length. So in this case, right, the idea is you can know the resistivity at this point in the slice. You can know its area and you know its thickness, ds. Well, if I go back to my standard formula, right, R equals rho L over area, the idea here is resistivity would be the resistivity at this location in the material. The length of this is dx in this case, or ds. And then the cross-sectional area would be pi r squared for this particular example, right? So far, so good? All right. Okay, and so that's actually bullet point 2 and 3. Length goes to ds. And then what's 4? Okay, usually rho is uniform. If rho non-uniform, plug in equation, right? And I'll describe that later if we have time. But the idea is like maybe rho would be rho equals 3x or something, right? I don't know. It'd be some, and we don't want to talk about that right away. We'll do it. That's our standard procedure. You ready to try one? Let's see. Is it 5:30? Let's see. When do we usually take our break? I forget.
45.
Close to 6, right? Okay. Let's try 26.18 at least and see how we're doing, and maybe we'll take a break. 26.18. I need to erase all this. You've got it in your notes. I'm doing it. Any questions from anybody before I erase? Okay, go to it. Check with your neighbor. You get hung up and you're waiting on me because I'm slow, then check the solution. But try to do it yourself. Talk as much as you want. (26.18) case 1. It's supposed to be a cylinder. Which way is current flowing in this one? To the right? Yep. And remember, current is not a vector, but we think of it like a vector. Gotcha. I know what you mean. Okay. So, do you think I need to use calculus? Yes or no? No calculus. Why not? Rho is uniform, which means not constant, basically, right, for us. Rho is uniform. It says that in the problem statement. Is the cross-sectional area constant? Yeah, what is the cross-sectional area here?
Pi r n. Pi r outer minus pi r n.
And I'm assuming you meant,
Yeah.
I know what you mean. which in this case, isn't that gonna be 3 pi r squared? Wait a minute,
Wait, two.
should I be careful with this capital R? What are the symbols we used here?
Orange,
A and B, do you agree? So I want to be careful here. This does not mean resistance. Do you agree?
Oh, yeah.
So let's make that a lowercase r for this problem. We got to watch out, and that's probably why I used R instead. I probably used A and B. So I want to be careful here that these are radii, not resistance. So it's going to be pi, I think, b squared minus a squared. All right. So then in this case, R, the resistance is going to be rho. What's the length in this one? Do we know it? It's just L. L over pi b squared minus a squared. So that's the easy one. We don't have to do calculus.
That's just the answer right there.
That's it. Piece of cake. All right. Now let's look at part B. Case 2. Trying to draw the cylinder with some perspective there. Right? So this is where the material is. That's the sidewall, right? Yeah. Current is flowing radially outwards. So help you visualize. You know me, I like me a set of nested PVC pipes and ABS. Is this even plausible? Imagine you take a battery and you connect it to this central conductor here, right? So it looks like this. Sorry, I'm trying to get this on Zoom. The idea is current would flow outwards and you could connect to this outer cylinder. So what is the cross-sectional area through which the current flows? Yeah, and just, what's that? Yeah, surface area of which part of the cylinder? Is it gonna be this little part that I'm tracing out, or is it gonna be the sidewall?
Sidewall.
Sidewall, right? So this is hard to draw. Jesse, can you see this?
Don't worry about it.
Well, just let me know. I could try a different
No,
color.
it's fine. Okay.
It's barely visible?
I can tell the difference. But it'll work.
Yeah, you don't have to see the color, but you can tell there's a circle there.
Correct.
That's what I needed to know. Is it too sloppy?
Yeah, there's lyrics. It's just hard to draw.
It's just really hard to draw this, right? The idea is, again, this is where it helps to have 3D objects. The idea is at any one point, the resistance is going through, first it's going radially outwards through this pipe, then through the next pipe, then through the next pipe. And so the idea here is the area that we need is this. So the area is what equation? Give it to me.
Yeah.
What is it?
2 pi r up.
2 pi r L. 2 pi r L. Got it. That's the cross-sectional area. Is that area constant? Do these pipes have the same sidewall area? No. Do we have to use calculus? Yes, now we know why. Okay, good. So in this case, what's the thickness? ds is now dr. It's a small amount of radial thickness. So if I can draw just one of these shells, right, the idea is the length of it is L. The distance all the way around is 2 pi r. And the thickness, right, this thickness here is dr. That's the length through which current travels at that cross-sectional area size. So now my resistance is rho dr over 2 pi r L. And we see how important it is to keep track. And this is one little chunk. What do I do when I want to get the total resistance? I add them up, integrate. What's the upper and lower limits for this case? A to B. What things in here are constants?
Everything but R.
Everything but the R. What is that integral? And this is one where it helps to have the limits. What do you
Natural
get
log
when you
of
do
R.
that? Yeah, log. Now remember, a physicist is always just going to say log because they're lazy. Unless they mean something other than natural log, they will specify it. So basically, we're going to say log and mean natural log. Okay. So, and then when you plug in the limits, what do you get? That's right. We get a natural log or log of B minus log A, which is log B over A. Right? Now, is this going to be the right units? How could we check the units? What are the units of resistivity?
Ohm meters.
Ohm meters. Excellent. What are the units of log?
Nothing.
Nothing. Function? How about 2 pi?
Nothing.
Nothing. So length?
Meters.
Is it ohms? Check. We're feeling good. It's either the units checking or those quaaludes I dropped about 20 minutes ago. I don't know. I don't know why I like to say, it's just a fun word to say, quaaludes. What's
Have
that?
you seen Wall Street?
Yes, I think I did, yes. Okay, I'll check that later. Anyways, yeah. All right, so, so far so good. Always the chemist, you gotta watch him. All right. Let's check another thing. Resistance, do you think it should be positive or negative? Positive, is it? What's that log term, positive or negative?
Positive.
How do you know it's positive?
The graph of log goes like up to infinity.
Yeah, but doesn't it also go down to negative infinity?
Yeah. Well,
What's the crossover?
yeah. Pi over 2, I think.
One.
No, I don't know. Oh,
1, right? Look at the graph of natural log, right? Think about it. Okay. E to the 0 is 1. Take the logarithm, you get 0, right? So if the input is 1, the output is 0. So for numbers less than 1, we would expect a negative result. For numbers greater than 1, is this number greater than 1? B was bigger than A. We're good. So this might be a decimal number, but it's going to be positive. Okay, that's all I'm trying to say. All right, feeling good on that? All right, should we try another one? Or do you want your break? What do you think? You guys call it. One more? All right, I like that. I like that. Suffer now. Oh, wait. There was one last part to this that I forgot. I just saw it. It says, for what length are the two resistances equal? How would we do that? Set them equal. All right, when we do that, what drops out? What else? Rho. What's rho again? Remember what that is called? Not resistance, but resistivity. So these two resistances would be equal whether I use gold or aluminum or cheese, because rho is the only thing in here that depends on the material.
Right.
So we see that if you could set these up, now you'd have to solve for L. What do you get? Let's just do it really quick. I think I get L is equal to the square root of something. Do you agree? Let's see, the pi's drop. rows drop. This L comes over here. So I think it's going to be B squared minus A squared all over 2 with a log. So if we use that special length for whatever reason, we'd expect these two things to be equal. And it doesn't depend on whether the thing is made out of gold or cheese or frogs.
Nice.
All right. What do you think? Now let's do another one. I'm going to leave 26.19 for you to do at home. That's the spherical equivalent. Again, every once in a while, these weird shapes. Does anybody know how this is used in the real world? I mean, it seems so obscure, right? When you're looking at it. What's that? Okay, although generally speaking, we're not running current, but maybe this helps us get a limiting value of drain current. That might be true. I have no idea. That's a good thought that I hadn't thought of. It's actually, that seems probable. This would be used in coax. What else?
I was thinking of how it's moving.
You could relate this to Geiger counters, or I believe what I heard was they do salinity checks of ocean water. And what they do is they run these cylinders through the ocean, and you can run current through it. And then you can use this calculation to say, oh, well, I know that the resistivity is in here somewhere. If I apply a known voltage and get a certain amount of current, that tells me the resistivity. So you could reverse engineer it to actually be a resistivity checker. And I believe that's how they do it in these seawater measurements. I always have a boat with one of these underneath it doing this thing or something. I vaguely recall that's true. If I'm wrong, well, sue me and hate my YouTube channel because it's got what, 3 subscribers? All right, I could care less, right? All right. Now let's try, I think we've really beat that to death. Let's try 26.20, all right, 26.20. Looking at this. And then just so they can see, I'm going to zoom in here for a second. The idea is we're studying this piece of material, and hopefully you can see that there's a different cross section. I'm looking at the Zoom people. You guys could start reading your homework. So just giving you an idea here of what this looks like. This is the shape in real life that I'm trying to draw in your workbook. Okay. I'll do this. Now let's go back to here. That's what we're looking at. Can't see it. There we go. Okay. Now, with these problems, check out what I usually do right away. Okay. One of the first things I like to do is get a coordinate system in this problem. You don't have to do this, but sometimes it's pretty useful. Now I'm going to draw my slab here. Not perfect, but we get the idea. All right, so there's my slab in 3D space. Put this over here so I'm not walking back and forth all the time. We've got some dimensions here. We're told that this is dimension A. That is dimension B. This is D. And this one that's kind of hard to draw here. C. All right. Now, as constant resistivity, so rho equals uniform, right?
Right.
So we don't have to worry about that right now. It says determine the resistance between the front and back faces. Okay, that's this. Right, between the front and the back. Is the area changing as you go from the front to the back? No.
No.
I go from front to back. Do I need calculus? No. So we can do this one really quick. So if I'm going front to back, this is part A, I'd say R equals rho L over area. Let's go through the pieces. Which of these dimensions is the length? If I'm going from front to back, what's the length?
C.
C. This is the length. It's the short axis is the length in this case. Isn't that weird? Right? I'm going this way. The length that I go through is actually C. Okay. How about the area? What is the area of a trapezoid? Somebody said it. It's this area, right? I'm going to draw a mini picture. It's this area. That's the cross-sectional area in this case. This is A, this is B, this is D. Does anybody remember the formula?
A plus B times height.
Close. No one remembers the formula usually, right? Watch this trick. Couldn't I take this little puppy here and stick it down in there and make a rectangle? So it's average height times the width. Well, in this case, what's the average height? A plus B over 2. That's what you forgot, Jacob. Got it?
Oh,
But you had the right idea. So it's A plus B over 2 quantity times what's the width?
C.
My report card had all A's. I threw some D's on it. Who sang that song? Does anybody know? My report card had all A's. Throw some D's on it. I don't. Yeah, I'm like, yeah. You haven't seen these physics student scores, have you? They're already D's. All right. Anyways, okay. Moving on. Moving on. Oh man, I'm mean. All right. That was supposed to be a joke. Okay. All right, part B. Let's get to part B. Get me out of this joke. Okay. Oh, wait, it was my report card had all F's, throw some D's on it. Whatever. You can tell I don't know these songs very well. Okay, so part B. Am I gonna have to use calculus? What do you think? Yeah, you can. Otherwise I wouldn't be doing it right. So R is equal to the integral of rho ds over the area. We're going left to right. So to be clear, we're going from this space here and this space here, right? Which way is current flowing? Some way like this. Now, to be clear here, do you agree the current would start to angle a little bit?
Yeah.
Somewhere in this problem, it says the angle is exaggerated, doesn't it?
Yes.
So we're assuming it's only slightly angled. We're drawing it lots of angle. What's the surface that I need to draw then? Would it be a vertical cut, horizontal cut, horizontal?
That sounds cool.
I need a break too. Which way am I going to slice this damn thing? Show me with your hands.
Vertical.
Like this, right? Yeah. So now I'm going to try and draw that. That's it, right? Well, what's this dimension? What's a good name for it? I heard, what did you say? Wait,
DX, sorry.
you said dx, right? Aren't you implying, usually don't we consider this as the x-axis?
Correct.
So unless we have some good reason to do otherwise, how about we call this the y-axis? This would be the z-axis, or actually, I don't know, maybe, let's do it this way. Let's say this is y, and that makes this, is it z or negative z? Z, all right. That way we don't have to think much. We're doing standard 2D problem. All right. So tell me again, what's this dimension? Dx, a small amount in the x. What's a good name for this distance here? X. I'm going that way. That's in the x direction. Why don't we just call the distance from the origin along the x-axis x? Sweet. What's a good name for this height? What'd you call it? Y. Is y a constant? Damn. How is y changing as we go around here? Is it a cosine function? Is it an exponential? Is it a parabola?
Linear?
Technically, it is a parabola. It's the special parabola where the squared constant is 0. Excellent. I'm reaching. All right, it's a straight line. Does anybody know any equations for a straight line? I heard y equals mx plus b. Why do I hate that in a physics class? For a couple of reasons. We have b in our math. M is mass for us, or meters. It's like, so I know you don't have to do this step, but why add confusion? A little bit of writing is not going to kill you. Let's write out the words. Slope x plus intercept, just so we don't screw up mass, meters, b, a, whatever. You know what I'm saying? You don't have to do that, but I do think in this particular problem, it will add some clarity. Otherwise, we're going to end up saying b equals a, and that's really confusing to me. Tell me a slope. How do you get slope in general in math class? What's that? Rise over run. In this problem, what is that?
Rise is b minus a.
The final height is b, the initial height is a. I rose b minus a. Money, 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 money. What's the run?
D.
What's that?
D.
D. I can't tell over Zoom if you're saying D. I'm going to assume you said D. All right. Is that good? Now, what's the intercept? Canadian says A. Don't you know A? The intercept's A. All right. Canadian's favorite intercept. All right. I think we know all the pieces to plug in. If you could just tell me what the area is in terms of this weird thing. What's the area I need? I know it's rho. I know it's dx. How do I get the area? Think it through. I want the area of this slab. What's its height? What's
Y.
its width?
Dx.
That's its thickness, so to speak. Because remember, current's flowing this way. We want the cross-sectional area. The area of this strip would be y dx, right? But the current's not flowing this way. So I don't want this area. This is not the cross-sectional area here. I need this big area right here. YC. Did that make sense, Jacob?
Oh, yeah.
See it? That's why it's important to remember all the time this is cross-sectional area. When we're doing integrals in calculus, we oftentimes call it y dx is the area of that strip. But that's not the cross-sectional area. That's not the area we need to do this calculation. All right. So because I'm going to run out of board space, I'm going to plug this in up here, okay? Everybody cool with that? What's our limits? 0 to what? I heard 0 to D. What do you think? What are we integrating over in this particular case? X. What's the smallest value X can take? D. Looks good. You had it. Just making sure. Sometimes when I'm up here, I don't have a good angle, so you can see it better than me. All right? Just check. Can't we plug this in and do the integral? What, how are we gonna have to do this? It's gonna be ugly, right?
We could substitute it. Yeah.
Rho pops out, do you agree? What else pops out? Give me all the constants. Rho and C.
Why do you?
Don't get out of the way. Isn't that it? Because Y depends on X, you gotta plug it in first, right? Or do we? Okay, I'm gonna show you a trick in a minute. Do you agree we can plug this in? What type of method would you need to use to solve this? What technique?
A U sub?
A U sub. You're lucky you got that. You didn't have to hear my joke about an underwater sea vessel doing calculus with female sheepmen.
What?
Oh, I guess you did. Okay, a U sub. Oh, it took me like a minute and a half to get that. That's how, yeah. So if you're from the morning class watching this, yes, I just threw shade at you, I guess. Oh my God. All right, good work, good work. They were right before lunch. I'll give them some credit. Now, do you agree you could do this with a U sub?
Yeah.
Let me show you another way. Isn't this Y right here? Isn't that basically the U sub? Do you see it?
Oh.
It's the U sub. So I'm going to show you another way. What is dy? If I took the derivative of this, right? If I take dy dx, what do I get? The slope. Do you agree?
Yeah.
Well, isn't that the same thing to say dx is equal to d over b minus a dy? Just rearrange that. Bring this over here, flip this and bring it over there. You get that?
Yes.
Well, can't I just plug this in this way? R is equal to rho over C times the integral of d over b minus a times dy all over y. What are the limits though?
Wait,
What?
they change. It's
Zero
like
to A, zero to B.
no, it's a plug in it's plug in zero.
What? Look at y.
Okay, what?
What is the smallest value of y?
Zero to B.
A.
Oh, bro.
What's the biggest value? It works. Put that in your crack pipe. Smoke it. See how it goes. All right. Now, this trick works for a lot of these problems, especially when the equation in the basement is linear. So the area varies linearly. So if you have a linear function, can you think of a shape that might not be that easy? This one, right? Okay. How are we doing? Now we should take our break. Do you agree? I'm cooked. I need a little break. So, all right, we'll come back to this. Any questions from anybody before we take our break? Okay, all right, go for it. Zoomers, any from you?
When are we coming back? 6:10?
Yeah, 6:10 on this
All right.
clock anyways, yeah. 10 minutes.
Sounds good.
this cleaned up. Probably gonna do 26.21 next, if you want to start reading. 26.21 is next. That's that sheet, right? So again, we're looking at this shape right here. And we're going to try and do the same process and see if we can kind of get this down. You probably know how to do it, so race ahead if you want. Oh, the first step usually gets people. I think this first step, again, I wouldn't be doing this if I didn't have a firm belief it was useful. In particular, I think the step that we're about to do, the first step, we're trying to describe a shape, right? Mathematically. This could be valid for any number of branches in engineering. Who cares about what we're doing that for in this context? Who cares about the resistance calculation necessarily? But the idea of correctly describing a mathematical shape is useful. Let's try and focus on that aspect of it. Okay. So in this case, coordinate system, right? We've got our slab. What are we told about this slab? It reaches its minimum at the left end. Parabola's minimum occurs at the left face. Now, the one that you see in the book kind of looks like this, right? Sorry, this isn't perfect. But the idea here is it's still got some depth into the page. It's just hard to draw that. Right? So it's like, it looks really goofy when you try and draw it. That's supposed to be the shape. Again, there's some thickness to it like this real life thickness. Right? And we're told that that dimension is once again C. We're told that this dimension is once again B and A and D. We're going from the left face to the right face, agreed? So we're still going to slice it in this weird ass way. Because the current's still flowing left to right. Okay? Current still flowing left to right. And in order to study this, we need to know this function for y. It's similar to before. We know that this distance, we describe it as x. We know that this distance here is dx. Everything looks the same. We're trying to describe that shape. If we can't get y as some function of x, we're toast. Well, part A says do that. So what is the general? Let's go through the process. When we had this shape, you looked at this shape and you told me an equation. What was the equation you told me for this shape?
Y equals slope times x plus intercept.
Right. What is the equivalent thing we could do for this shape?
y equals x squared plus intercept.
Okay,
Maybe not.
that would be good for one special parabola. It happens to be correct, kind of ish, for this one. What's the general, it's a parabola, right? That means y is equal to, we know there might be an x squared term. Could there be an x term in a parabola? Yes. So what we might do, could there be a term with x to the 0? Yeah, so why don't we call that constant 0? The idea is we write down the general equation for a parabola now. So instead of y equals slope x plus intercept, we write down, here's a general form of a parabola. Someone else might say, no, I disagree. I would call it some constant times x minus x naught quantity squared plus some other constant beta. Let me turn that off. Sorry about that. Old school. All right. Oh, I should have put them up here, Mike. That's my my friend that does the quantum computing at the Amazon. We should have made him join our class again. Let's see if he can guest speak later. All right. So in this case, oh yeah. Anyways, do you agree? 3 constants here, 3 constants here.
Yeah.
Maybe you don't think this way. Whatever. I gotta say, I like this method of thinking of a parabola because in the real world, couldn't you just punch in some numbers in Excel and play with them until the shape looks like what you want? And then when you do that, you could go out into the field and pour concrete into a mold that has the right shape.
Yeah.
That's what I'm thinking in my mind. I could make a parabola that looks close enough in the real world with this format and just play with the constants. So I'm going to use this one, okay? Now, how can I figure out these constants? Any ideas? I need to figure out the 3 constants and then I'm golden. What's one thing, any ideas?
A naught would be A.
You said K naught equals A. How did you know that? Kind of,
Well, I'm kind of connecting it to the intercept, and that would be sort of where
Let me-
A is minimum. So
so the intercept means when X equals 0, you told me that Y is equal to A. Isn't that what the intercept means?
yeah,
So what we could do is, this is in general called a boundary condition. So what I'm doing is I'm plugging in the result at the left boundary to determine one of the constants. When I plug this all in, I get A equals K naught plus, when I plug in X equals 0, what do I get here? When I plug in X equals 0 to this one, what do I get? Isn't he correct? We now know one of the constants. Sweet. What's another boundary condition I could employ? Say again? B? What about B? How do we get B? What would be the equivalent statement that involves, you said B, right? What's the equivalent statement that involves B? When X equals D, Y equals D. That's the right boundary condition. All right? Those of you that had 162, do you recognize this from quantum mechanics, particle in a box? This was what you did. You did boundary conditions. All right? Gee, I wonder where this might be useful. All right. So in this case, let's plug it in. So Y is equal to B. When X, you're going to get a D and a D squared in there now, right? Okay, so I'm going to say that this is. And didn't we already learn this first constant is A? Shoot. That doesn't get the job done. Why not? We've got 2 unknowns, right? So K1 and K2, damn it. How could we get another boundary condition? We were told another thing about one of these boundaries. What was the other thing we were told about a boundary? Read the words carefully. The boundaries are the left end and the right end. What's the other special thing we know about either the left end or the right end? What's that?
That's the basis. So
Minimum, something about minimum. That's a special attribute of the function. We're told the minimum occurs at left end. Well, what do you know about the minimum of a function? Slope is 0. Slope equals 0 at left end. How do I get slope? Derivative. Right? You feel that? In this case, let's see if that helps out. Well, what's the derivative of this function?
2K.
Yeah, K1 plus 2K2X. And we say that's equal to, how about I just call that? Right? And now what am I going to do? If this goes to 0, we're told this goes to 0. K1 is 0. In Physics 162, you're going to see these boundary conditions appear a lot, where they say, oh, the values at the left and the right end have to be this, and certain things about the derivatives have to also be true. All right. All right. So in this case, that makes this a little bit easier. There we go. So what is K2? A big, big mountain. You're going into the death zone, bro. What is that? Chris O'Donnell? You guys probably don't know this movie. Do you know what I'm talking about? This is like a bad rock climbing movie. You're going into the death zone, man. All right. K2. Yeah, thank you. Get me out of this damn thing. Jeez. All right. At this point, the problem is no different than the previous problem. Do you agree? We still have, if I could squeeze it in here, I can't. If I write right here and get this out the way. Can you see if I write right here? Good. Yeah, all right. Now what could we do? We could say R equals the integral of rho dx over yc. And then we could take this thing. In this case, I don't think our trick is going to work. We'd use the function. And then what would our limits be? 0 to d. Right? Same problem, boring from that point. Pretty much. Yeah. Okay. Okay. I'll leave the rest of this for you to do a little bit at home. Let's say, but I do want to talk about part D here. Part D asks, let's say I just wanted to get the resistance between the front and the back faces here. Oops, I lost my slab. The detritus of the class gone bad. All right. All right. So I'm saying, let's say I want to get the resistance between the front and the back. Do I need to use calculus? Yes. Do you know the area? Gotcha. The area is constant, but you need to use calculus to figure out the area. That's the one where you do the y dx and integrate, right? Gotcha. Oh, that crazy physics. Isn't that fun? It's like, oh, damn. These are the things you think about when you're drawing all these pictures. Because it takes so long to write, you get a lot of time to think. All right. And then explain what would be different here if this was non-uniform.
Plug in.
You'd have to plug in some function here and you couldn't just pull out the constant. Everybody got that?
Exactly.
All right, all right. Now, you know me, I love to see the light, the students' faces, light, whatever that bad joke is. Gosh, it's not that fun. Let's do one at a time so I don't screw this up. Doing some demos. Don't do your own home wiring, okay? I can, you can't. All right. What's that? Well, I don't want students to die. That's basically it. Unless I'm grading their tests. Why? Why? Did you guys see me during the test?
Yeah, I saw your face.
It's just like, you guys, what are you doing? Drives me nuts when I'm like, whatever. It's like, it's a lot easier to do these problems if you've done them for 25 years. Or whatever I did then. I don't know how long it's been. Surely this home wiring with a bunch of paper towels next to it couldn't be dangerous. All right, now, you know a little bit about circuits, and let me see if I can, you guys out there in Zoom land need to see. Give me a minute. Got it? Can you see that?
Perfect.
Okay, we got two circuits. I'm guessing you can tell which one's in series and which one's in parallel, right? So this one, series or parallel? This one, all right? You can see it, if I hold it up, you can really see there's just one loop there, right? So my question is, in both of these circuits, there's a six, why don't I rotate them so they're the same way? There's a 60-watt bulb and a 25-watt bulb. So in a minute, I'm going to turn these on, and I want you to figure out which one should be brighter. Gee, talk amongst yourselves and see if you can come up with the answer. 60-watt and a 25-watt. All right. Let's start here with this one. This happens to be the one that I've got right here. So we're looking at this case, which is the parallel. When I turn these on, which bulb is going to be brighter, the 60-watt or the 25? What's your gut tell you? Are you correct? Yes. Great. All right. Same circuit. Well, no, different circuit. Now we're going to this one. They're in series. You got a 60-watt and a 25-watt. Which one should be brighter? Go with your gut. You want to say 60, but you know it's physics, and I took the time to do this, so what's the answer? What's up with it? Huh. All right, and let's just make this a little bit more dramatic so you can really see this. Whoops. Right? In the parallel circuit, this is clearly brighter. Now, you might not be able to tell much in Zoom land, but if I stick my hand here, I think you agree, out in Zoom land, this one is definitely not as bright. Huh. Now, obviously, there's some manufacturing inconsistencies here, but these bulbs should be pretty close to the same, and these bulbs should be pretty close to the same. Right? So it's like, why is this so different? Well, let's see if we can understand this. All right, so let's go to the board here, and we'll come back to these in a minute. So let's go to the board. Any questions from Zoom on that? You got it? Ready to talk about it?
Yep.
Okay. Reminds me, we're talking about resistors. Okay. And maybe I'll give us a micro review. Okay. I'm going to talk about capacitors because that's what we learned already. When we did capacitors, what was our two main equations? Q equals VC. What was our U equation?
1/2 VQ.
Then what did we do with this equation?
Substitute.
We substituted in two ways. One of these equations ended up being Q squared over 2C, and the other was delta V squared C over 2. Why did we discuss these? Do you remember? What was the benefit of this one in general?
For series.
This was same charge or series, right? Things in series tended to have the same charge. What was this one for? Same voltage, same delta V, which tended to be for what type of circuits? All right. Remind me of the comparable laws for resistors. What was the equivalent? Yeah, Ohm's law. What was it here?
R, V equals IR. Yeah.
What was the equivalent to energy? This one, we have a dq dt. What do we get when we take du dt? Christopher Walken, James Bond movie, tried to raise the blimp. He says, I need more power. I need more power, guys. Now I'm forgetting how to spell. It's a weird delta. That delta's moving places. All right. Power equals IV. What do you think I'm going to suggest we do immediately? I heard I squared R. Huh, that's going to be good when things have the same current. Things in series tend to have the same current. Huh, what's the other one? Same voltage, parallel, right? Well, I wonder, let's say we want to analyze one of these circuits. Give me a sec. Can you still read the board, people on Zoom?
Yep.
Got it. Money. Here we go. Let's say we want to look at this circuit here. It's a parallel circuit. It would be wise to use this? Probably, right? Well, which one was brighter? 60 watt
60.
brighter in parallel. So you just told me 60 watt brighter in parallel. What does, well, I wonder, brightness, watts. Brightness and watts represent power. So you just told me power 60 watt is greater than power of 25 watt. What does that tell me? Well, I guess I should say one other thing. What voltage is implied when we use this circuit? We're plugging this into the wall socket. Does anybody know the voltage we assume for the wall socket?
240.
Nope, that's for three-phase. That's for like laundry machines and stuff.
Oh God.
120.
Oh,
If you're Euro style, then you're 240 as well. All right, so European power sockets, I think, are 220, 240, something like that. All right. Now, to be clear, this is not a battery. It turns out it's actually oscillating between 0 and 180 and down, but on average, RMS, whatever, it's 120. We'll discuss that later. If you don't believe me, talk to me in lab tomorrow. Okay, I don't want to do this on video. Okay, I'll show you this. We'll give you the electrodes and we'll have some fun. All right. Now, in this case, just trust me, this circuit is equivalent to a 120 volt battery. I'll prove that to you later this semester. Huh, what does that tell me about the resistance of the 60 watt? versus the resistance of the 25 watt. Use this result. Don't they have the same voltage because they're in parallel? Are they equal? This one's brighter. What does that tell you about its resistance? You just told me this. In order to get more power with the same volts, I need less resistance. Should we be able to check that with this series result? Look at the series result. Which one's brighter? Clearly the 25. This one, you can barely tell it's on. I could prove to you that it's on. How could I do that? Now it's open, right? Clearly there's current flowing through here. It's just not enough to heat up the bulb enough to make it light up. You know what I'm saying? This is a long skinny wire in here. All right, all right. So in this case, the 25 is brighter. So in series, it's hard to read. This one in a while. In series, what did we find? The power of the 25 watt was greater than the power of the 60 watt. It was brighter. It had more power delivered to it. Well, in this case, what does that tell us about the resistance of the 25 watt? Let's use this. In series, these things have the same current. What does that tell us about the resistance of the 25 watt? Bigger than or less than R60? More power, same current. For this number to be bigger, that has to be bigger. Is that consistent with that answer over there? 25 is greater than 60 is the same thing as saying, or resistance of 25 is greater than resistance of 60 is the same as saying resistance of 60. Yes. Check. In theory, which of these circuits would be good for calculating the resistance of the light bulb when it's in operation? Which one has a number? Do you know the current right now? Do we know the
Delta V1?
voltage? Ding, 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 ding. Know the powers, know the voltage, we got this. The ratings on these bulbs only make sense if you're using parallel circuits. What's the advantage of parallel circuits? How did we check if this was on?
Oh, if you unplug it,
Right? There's the same voltage across. Isn't it convenient that when you turn off a light switch, your refrigerator doesn't stop working? So why do we wire houses in parallel? I wonder. Now, look carefully here. These are supposed to have 120 on them. Watch this light bulb super closely here, right? You see any changes at all? I don't see much. Do you? There's probably a very tiny change. We're all the time ignoring the resistance of wires in these circuits. But in reality, the wiring in your house is long enough that you may actually be changing the resistance slightly. So because there's this, remember R equals rho L over area?
Yes.
The resistivity of wiring is a very small number, 10 to the minus 8 or nano-ohm meters. But the length could be many, many meters in your house. So what we do is we try to make the cross-sectional area big enough such that the wiring in your house has negligible resistance compared to the devices operating in your house. But if you've ever been in a house and turned on one light switch and another and a fan, sometimes you'll see a light dim or just, right?
Yeah.
These things can happen. We'll discuss that a little bit later. Typically, when does that happen? What types of things are you turning on and off when you see the lights dim? Do you notice?
Vacuum cleaner.
Vacuum cleaner, or maybe a fan, right? Things with giant coils of wire in them. Motors. We'll learn more about that later. It turns out when you turn on a motor, it opposes you turning it on. Because a motor acts like a generator in reverse. So when you turn on a motor, it actually acts like a generator that opposes you turning it on. And for a split second, it opposes the current flow. Well, it's 6:40. My God, we're done early.
What?
This is disturbing.
What? How did it-
Luck. Maybe it's because I got here extra early and
Right.
remembered to set this up. I finally remembered for once, oh yeah, I gotta do Zoom today. I try not to think about Zoom. So I am cool with answering any questions, or if you want to just run away screaming or not screaming, that's cool. We can do another sample if you want, or, oh, I know what we should do.
Yeah.
One last thing, let's foreshadow. Okay, so just to look at this and then we'll get out of here. We'll be done 5 minutes early. Okay, we're talking about power. Wouldn't it be nice if we had a set of rules that summarize these things?
That'd be
What do you bet it's 2 pages down in the worksheet? Let's take a look. Go to page 117. I'd rather do an extra problem than leave personally, right? If you got it, I believe, page 87 is the other sheet, the capacitors. Kind of look back and forth at those two while I erase really quick, okay? Try to see, look for similarities and differences. And there's one key difference that we could emphasize that I forgot to write on this board. That's what I remembered. I'm like, oh yeah, I should say this. Remind me of some physics equations. What's the capacitance equation for a parallel plate? Epsilon naught
A over O.
A over D,
Oh, yeah.
usually. But yeah, at D length, same thing. What's the equation for resistance we've been using all day?
Resistivity. D L.
Rho L over area, right? Look at the area of these equations.
Yes.
It's flipped. Look at the length, so to speak, flipped. This is why caps in series, when you're dealing with caps in series, you're basically extending the gap, right? You're making the gap bigger, you're increasing D. That's why we get this 1 over CEQ equals 1 over C1 plus 1 over C2 plus 1 over C3, dot, dot, dot. Well, think about resistors in series. We've discussed this already today. I alluded to it. We're basically just extending the length. That's in the numerator. That's why in series, we use REQ is R1 plus R2 plus R3, etc. So this is why the series parallel rules change. What doesn't change? In series, things have the same Q. Well, if I take the derivative of that, I get current. So what? All right. And so, all right. And I think this helps me figure it out. And then remember, always, always, always remember, I want you to associate this word parallel with what other words? Voltage or delta V, right? So parallel, same delta V. Now, I don't know if you can tell here, when you put things in parallel, maybe let's do this on the other board just to make sure we're good on this. In parallel, I'm going to try to draw these capacitors as 3D now. Right. The idea is if I put two capacitors in parallel, I'm extending the area. Right? The area doubles. So caps in parallel, we're going to get the areas on top. Whereas resistors in parallel, Think of two wires or two cylinders. Right? Areas in the basement. Right? Areas in the basement. So what do you think our rule is going to be for these in parallel? 1 over REQ. So far, so good on that? Okay, good. Now, let's do one super quick problem with this. I know you guys want to go, but if we get this done now, that means a little bit more later, and then maybe the day before the test, we'll have time to review, right? So 10 minutes of reviewing for a test the day before is worth a lot more than 10 minutes off now, in my opinion. So let's crank, all right? Let's do it. I'm gonna make up a problem with numbers just to get a feeling and see if we're starting to get better at this. I got a 9-volt battery. Let's say I have a 10 ohm resistor. And actually, I'm going to say a 12 ohm resistor, I think. I've got a 24 ohm. Oh, geez, that's sloppy. A 36 ohm, just some random resistor values, whatever. Okay, can you see that on Zoom okay?
It'd be good just a little to the left.
How about that? Good enough?
Yeah, that's fine. Yep.
All right. What's the first thing you would do, people?
Take care of the parallel.
Take care of the parallel. In this case, we're going to combine these two in parallel, right?
Yeah.
What's the shortcut rule I could use for these?
R1 or 2,
Punch it in. What do you get? 14.4? Sounds good to me. I'm trying to remember the value from this morning. Tell me if it's 14.4 or not, okay? I got to erase anyway to catch up. Confirm that number for me, will you?
Yeah.
All right, good to go. What's next? Series. All right, so we just add them together. What are we going to get there? 26.4?
Yeah.
This is a 9-volt battery. Hey, we got one circuit element left, right? What does that tell us? What do we know about this device now? There's the battery and it. They're the same voltage. Right? So now in this case, this is 9 volts. What equation could I use? And what could I now figure out? Yeah, okay, I know delta V equals IR. I'm going to write that down. Hold on. Do we know resistance?
Yeah, we do.
Yep. Do we know voltage? So we could get current this time. So in this case, punch it in. Give it to me. Maybe I'll just put this. That way we know.
0.341.
0. What?
0.341.
Units.
Amps.
Amps. What is this in milliamps?
320.
What do I bring back? I'm going back the other way now. This was a series combination, right? That was series. What do I bring back? In series, things have the same charge, okay, which is the same current. So this is now 341 milliamps. 341 milliamps. What equation could I use and what could I determine? You could get the voltage now, because now I know I and R. Okay, what do you get? Let's just say maybe this is 4.95. This is 4.05. Somebody check those numbers real quick.
You think you can do it?
Nope. Yeah, because remember, this is a 9-volt source. What do you get? Just confirm one of them. If we get one of them, we know the other's right, because they. Good? Appreciate it. I'd have to find my calculator. I'll be slow. I wonder what I did with that other one. 4.91?
On the bottom.
Okay. Oh, because of rounding probably. All right, so we got a 4.91 here, something like this, all right? So that means this must be 4.09. Do you agree? How do I know that this and that? They add up to the 9-volt source, right? All right. Do you agree you could get power, poison ivy, or I squared R, or V squared over R? What do I bring back to this home slice over here? Parallel. All right, you good? And then here, this would be 4.91. Do I need to write anything up here, or have we figured it all out pretty much? I pretty much dialed that one in. So then here I could get the currents, right? Let's do it. What do you get for the current? So I need the V over R. So turn it on. 4.91 div 36, 136. Or 136 millis. Okay, and let's say, what would this one then have to be? I'll just figure it out.
2.5.
What should they add up to? 341. If you were doing this circuit, would we need to worry about blowing a fuse if I was measuring these currents? Anytime you exceed 200, we'd have to go over the 10 amp setting, right? All right, so, all right. Generally speaking, what do we notice about resistors in series? When they're in series, which one has the higher voltage? The small resistor or the large resistor? Yeah, what's an equation we could use to interpret that? Delta V equals IR. Well, in series, things have the same I. So the larger R has the larger V, et cetera, et cetera. You could go on all day. Let's get the heck out of here. Sorry. Oh, man. You almost got out early and then I kept you late. That's total Jorstad. Oh, my gosh. Any questions from anyone on Zoom or you guys? Sorry about that, everybody. You got another problem in? That's you can really dial this in now. You guys take off. Sorry about that. I do apologize.
I have a quick question about the pre-lab.
Yeah.
Do you want us to write a separate intro procedure for each part, or can you do it all in
You
like
can just
one?
do one. You can say intro part 1 and part 2. Yeah. Like, so just
Okay.
intro and then part 1. And remember, try to follow those guidelines. And the idea is by doing your first draft, right, when you come in, I'm going to try and fix it. Please, 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 when you write those drafts, double or triple space it. Here's the idea. You have to do handwritten. But the idea is if you handwrite and you leave space, when you come in tomorrow and I say, dude, you totally screwed that up, I'll say, stop, write this instead. And you can just write it in the empty space. So that will keep you from having to rewrite. So if you write no typewritten, it's got to be handwritten. All right. All right. Did that address your question?
Yeah.
Yeah. So take your first stab at it and then you'll get out of lab faster because I'll be like, oh, you screwed up this, this, and this. Try it this way.
So we do like one part per page?
Yeah, so
Some of them
like
might take-
basically, when you finish the intro, don't start the procedure at the bottom of the intro. Start it on its own new page. That way at the end, you can reorder them.
So
really
do
easy.
part 1 intro,
Yeah.
part 1, part 2 intro, procedure, part 2, part 3.
I would just do intro, part 1. Actually, when you look at the intro, there's basically 2 equations to explain,
Oh, okay.
right? So you can just explain those 2 equations and then the procedure will have 2 parts, basically.
Oh, okay, so just do the, just normal thing. do an
Yeah, it's like
intro,
one
whole thing.
paragraph. Yeah.
of the whole lab and then part 1, part 2.
Yeah.
Got it. Sweet.
And when you're making an intro, just kind of think it should look kind of like a physics textbook where there's some words, an equation, and some words.
Kind of figure you want just like how we do in chemistry and stuff like that. Basic.
I don't know.
procedure.
Yeah,
Or the basic what we're doing in lab.
yeah, but I have very specific.
I'll read the guidelines too.
Yeah, because like I'm specific on what, like you have to do third person, past
Yep.
tense, no bullets.
Yep.
That, yeah, if you got that,
Yep.
think,
I just gotta work on it because
yeah,
I do the second person one.
yeah, just don't tell me to measure, right? Say, resistance was
That's
measured.
measured.
Back, yeah.
Awesome. Take it easy.
Right on. All right. You good out there in Zoom?
Hey, Jorstad.
Yep.
So I asked, God, what's his name? I only know him in Discord. I think it's Christian. I asked him
Can I stop
to,
the live stream real quick?